In about 5, 4, 3, 2. We're probably live now.
Hello.
And feel free to address the people in the room because they're the ones that are here with the boards. Don't worry about the camera.
All right. Welcome to the Utah Rust Blue Pill Workshop. Woo! So this is the third annual attempt at doing it.
Every time it gets better.
It's been crazy every time. I wasn't even here last time. And first time was like the beginning of COVID and like half remote, half local. It was a mess. So hopefully this will be the best one yet.
Yeah, because this is the least pandemic-y attempt.
Yeah, exactly. So, first a little bit about me. My name is Levi Pearson. I have been doing Rust for a while. I do Rust professionally for Red Canary, a security company. Previous to that, I did embedded systems development, but mostly in C. So my embedded systems Rust stuff is all hobby level. But I am excited about Rust for embedded systems because I was not really satisfied with C. It lets you get the job done, but it didn't help a whole lot, and it's very error prone. So when I learned that Rust was going to focus and make embedded systems first-class citizen, I was super happy about it. And I've been watching the embedded systems working group really closely, and they've made just amazing progress, specifically over the last year. So things are way better than they were when we first started doing this. People are using some of these tools professionally now, and
yeah, is there anything that we know that's been in production that's using Rust?
I don't know off the top of my head. There's probably some things, but anyway, next we'll introduce the blue pill, the star of the show. You have to remember not to use gestures. Okay. Okay, this is the blue pill. Specifically, this is the pinout diagram of the blue pill. The story of why it's called blue pill is detailed and long, and I don't remember it all. So I think there was a red pill previously that was kind of the same form factor. Anyway, it is sometimes called the STM32 F103 minimum development board if you want to search for it on AliExpress or one of those sites. You can pick up extra ones by themselves for, maybe $4 plus whatever shipping from China is these days. You can buy them locally, but the prices are starting to go up with chip shortages and stuff. Okay, the actual microcontroller part is this in the middle. We've got a USB port up here. This down here is the debugger connections, and those will become very important very soon. So you'll want to find those. We have a power LED. We have a user-controlled LED. This is the main external system clock. This below it is actually another clock. It's a 32K clock versus 8 megahertz. Typically you have a 32K clock hooked up to the real-time clock inside the system. We've got a reset button, which is always handy. And along the side here, we've got pin headers. They're 0.1 inch between center, which is the same header spacing as your typical pin header things, and solderless breadboards, and all sorts of connectors, and so it's very handy for doing prototyping. So this diagram is going to be super helpful for you because it tells you all of the different capabilities of each of these pins. Each of these pretty much goes straight to one of these pins on the microcontroller itself. And they all have a number of different purposes that they can serve. We'll get into it more later, but as you can see, there's a lot of variety over here. Some important things to note are where the power connections are, because when you're plugging in things like the rotary encoder or the OLED display, those will need power. And you can see here you can get 3.3 volts, which is what most of the things need, either up here or over here. There's one here, and then these two right here are also 3.3 volts. And then you have your grounds. Everything you connect also has to have a ground. Grounds are very important because they provide a signal reference. So if you try and connect two things without also connecting their grounds, if signals without grounds don't work. One of them will float higher or lower than the other ones. Everything will get confused. So you always got to check your grounds and keep them as tightly coupled together as possible. But yeah, that's the blue pill. We're gonna move from talking about the blue pill and the microcontroller for a moment to a little walkthrough of the kit components that we have available. Actually, I don't know how well that's going to work with my connection, but we'll then do a quick walkthrough of the internals that you can't see from the pin diagram, the architecture of the insides of an STM32. And then we'll start looking at the code for a basic Hello World sort of project. And hopefully at that point we can get everybody to the point of being able to run the code. And so, yeah, let me see if I will be able to get those pulled up with my potato internet connection. So if you want to follow along at home or at your seats, you should have gotten a link to this Gitty instance. Oh my goodness, that's going to take forever. Anyway, eventually that will turn into a picture of the blue pill.
I will try to post these links in the chat. Oh, we already got it going on.
I
Great.
gotcha.
Cool. And I'll cross-post that to the YouTube and Twitch chat for the few people that are there.
Yeah, you'll want to find this repository and this wiki link because it will have links to all of the useful information things. So we've got a pinout diagram, which is what we were just looking at. We've got the full schematics for the board. And then these three right here are manuals provided by ST, which is the company that makes the microcontroller. These have incredibly detailed information about the internals of the STM32 F103 chip, as well as the whole STM32 F1 family and the ARM Cortex M3 CPU that's the heart of it. Okay, important thing number 2 is the ST-Link V2 clone debugger. This is not a genuine ST-Link V2, but it runs the same firmware and it's the same microcontroller, so it pretty much works the same. So the important thing to note is that you've got a diagram right here. That diagram shows you which signals correspond to these pins over here on the right. If you take this view and you rotate it left, so you're looking down at the pins, you will, that's what those pins correspond to. And we're going to need to connect these pins here to the pins that I pointed out on the pinout sheet that are poking out of the back of the board. The right angle header, those are where you connect those wires. And you need to be very careful that you connect SW clock to the clock signal and SWDIO to the SWDIO, ground to ground, and 3.3 volts to 3.3 volts.
So quick note on that I want to make mention of. These kits are not all exactly the same. They came from different manufacturing runs. So don't pay attention to the placement of where he is going to show you to put it. Pay attention to what words are on both the board and the connector.
Yeah.
In theory, they're the same board, but in practice, they change things or they give us a different brand that will be different colors.
Yeah, the blue pills themselves generally have exactly the same pinout. These debuggers are not as standardized, unfortunately. So, fun fact about these debuggers is that they actually have exactly the same microcontroller as the blue pill board inside them, or a very similar pin compatible one. So with, I mean, you can put alternative firmwares on them if you want to mess around with different debuggers and that sort of thing. So we do have some links here to a couple of different pinout diagrams for some common options.
Where is it? Where do we flux actually? I think, yeah, well, it's back. So the same way it's
So that's what we want.
What are you looking for?
apparently mine's laser engraved backwards compared to everybody else, so it's sort of hard to
No.
figure it out.
I need my reading glasses.
Here, you can use mine.
Yeah, it makes it sort of hard having to find your glasses.
Yeah, you can
You can see stuff fine. It's like another person problem.
All like, my room desk is like in the bedroom as well, so like my wife will come in randomly when I'm like in the bathroom, turn off the light and take a nap, I'll come back in, or like if I took off my glasses for whatever reason.
It's actually
It's dark. I'm nearsighted.
Oh,
I cannot see.
so if you look at
Not
the
necessarily, it's just like crap word about
So
it.
the diagrams
It's dark in the room.
there's links to
I'm
diagrams
feeling for it.
and
And
it
that's
should be one of those two. I've got a multimeter so you can verify which ones have power and which ones don't. So
Yeah, we're the best of both worlds on this.
Oh, fine, me too.
Because I make it look easy, but I'm also distilled down the steps.
The LASIK Institute.
all right, so there's some more pieces of the kit to talk about. We've got an OLED display. This is a 0.92 inch monochrome but two-color display. There's a link to the manual for the controller of the display. You probably won't need it because there's some really great libraries that we can use. And here we have a rotary encoder. The OLED display and the rotary controller together give you the basis of making nice user interfaces for some kinds of peripherals and things. Yeah?
So it's like the same thing, so I have like a synthesizer.
Yeah, these are the kinds of knobs that you can just keep turning forever. They don't have end stops, and so you can turn them 360 degrees many times. They work on the principle of having two switch contacts that are sweeping across some interrupted contact traces, and so they flip on and off out of phase with one another. So you have those two wires connecting to the blue pill board allows it to detect both which direction and how far you have rotated it. But they are a relative distance device. So you don't get an absolute position, you get a relative position. So wherever it starts up, that's 0. And you can turn it right and counts up, turn it left, it'll count back down. We've got examples. Yes. I'm not sure, we'll get to them after we get a little bit further with everybody to the hello world blinking an LED point. So we've also got these 6-axis gyroscope accelerometer chips. Those are also I2C peripherals. We'll talk more about what that means. These are some thermal comparator switches. This right here is a thermistor. We've got a pot that lets you adjust a set point. This is an analog comparator chip. You hook up power and ground, and then whenever the temperature reaches the set point, it'll turn the digital signal here either on or off, depending on what direction it's passing it. So we've got links here to the description of the board and the data sheet for this comparator IC. And then various wires, LEDs, and buzzers. So that is the hardware. The next, we're going to talk a little bit about the internals of the blue pill. Where was it? Okay. All right, so this is a little block diagram of the internals of the STM32 microcontroller. So if you've ever looked at block diagrams of computer architectures before, it should be kind of familiar in that you have a CPU right here, and there you've got some buses, and you have memory and stuff like that. There are some differences, though, in that in addition to the CPU, you've got a DMA controller. These are both capable of initiating transactions by themselves. The CPU runs the show, but it gets its instructions from flash memory, and then it has some static RAM to use as scratch space. So while your PC, when you boot it up, it loads all of its programs and runs them from RAM, but then you've got a whole lot of RAM on your PC, and our blue pills have 20 kilobytes of RAM.
Wow, that's not a ton.
Yeah. But the thing that makes that less constricted than it sounds is that you also have this flash, and it looks to the CPU like it's just memory, except it can't write to it. So it's basically like a ROM chip that you can reflash.
So your executable bits stay in flash, they don't get loaded into...
Exactly. So your program and its static data, all the stuff that's not going to change, that just sits in flash. And SRAM is reserved for your stack and any runtime variables that need to change.
How big is the stack?
It's as big as you need. Whatever's left over after you have your stack variables or your static mutable variables allocated.
Oh, just one. I think on Linux it's like 8K.
Yeah, there's no fixed limit. There's no operating system unless you add one. So
8 megs.
8 megs?
Yeah.
That's right.
These write to, what am I trying to say? These boxes right here are the peripheral buses. So these are like the PCIe slots in your PC, in that they're where your expansion peripherals go. And all of these boxes right here are the special purpose peripheral controllers that you can use to communicate to the outside world. These are the things that connect to all of the pin headers on this side of the board. We have GPIO, which is responsible for controlling what the pins are used for, and you can directly from software read the state of a pin or write to it and set it to the logical state that you want. We have one of the timers is on peripheral bus 1. We have the serial peripheral interface 1. We don't currently have any of the peripherals that work with this interface, but it can be used to drive the smart LEDs like NeoPixels, as well as lots of other things. The USART, the Usart, is, you've probably heard of UARTs before, serial ports. This is both the A in UART means asynchronous, but this has an S as well as an A, so it's a synchronous or asynchronous serial port. You don't need to worry about that right now. You can just know that you can attach it to any USB serial port and do serial communication. These are really handy. They're the analog to digital converters. That means you can hook up any kind of sensor or like a joystick or something, or a potentiometer, that's something that has sort of a continuously variable voltage, and you can read what that voltage is periodically. And in fact, you can read it very quickly. I think you can go up to a sampling rate of 15 megahertz or something like that. So there are projects where people do things like little toy oscilloscopes and things like that. So on peripheral bus 2, we've got more timers, more serial ports, another serial peripheral interface, and here's one that we're going to use a lot. It's the I2C driver. This is a 2-wire serial communication protocol that a whole lot of chips use. It lets you write to a number of different devices on the same bus that respond to different addresses, and you can access registers within those devices and control them. This is how the Oled display is controlled, and also the accelerometer. And finally, another really handy peripheral is USB. You can configure this to be a USB 2.0, I think it goes up to full speed, so 48 megahertz. Yeah.
Can this be a USB host?
No, it isn't. Some of them in this family, there's like the connectivity line or something they call it, have things like Ethernet and USB on the go. This one does not.
Can it emulate devices like HID devices?
Yes. That's the primary use, is to function as a USB device. And you can make it be pretty much any kind of device you want, and there are handy crates and example codes for doing that. We won't be covering any of those right now, and there's a caveat with using USB, in that a lot of these boards have a manufacturing issue where they put the wrong size resistor on some of the USB lines, and that makes some USB ports unhappy with it.
If I'm not mistaken, we tested these and we found that they do work, correct? Remember? I'm pretty sure we tested these for that problem and found that there was only one out of the first batch that didn't work and the rest of them didn't.
Yeah. I've, in the hardware setup link, there's, at the very end of it, there's a little section on the USB issue. So if you run into problems getting your computer to recognize it as a USB device, look at that, and there's a couple of different approaches for figuring out how to fix it.
At the beginning of this diagram, you said, what is DMA?
DMA is direct memory access controller.
It means you don't have to have software to tell it to copy a file or a piece of data,
Right.
but it can copy it independently.
There's a lot of times when you need to move a bunch of data from one part of the address space to another part of the address space, and you can either like run a memcopy command that's a loop that basically occupies the CPU doing all that. But the DMA controller is basically a hardware loop, a hardware memcopy loop. You program a source and a target and a size and say go, and it'll do it. You can also program that in advance and set it up to run a sequence of copies and loop back and continue doing it. And it can be triggered by software or by a number of these peripherals down here. They can say, oh, hey, I have some data. And they send a signal to the DMA controller. The DMA controller says, ooh, I'm ready to run my program. And it'll copy a bunch of stuff from the region of these peripherals into some buffer that you set aside. And
This is like just standard embedded
yeah,
thing.
yeah, it's even in PCs. DMA controllers have been common in PCs and embedded systems and whatnot for a long time. That there's something that's usually handled in the operating system, so you don't, as a user of a PC, know much about DMA unless you've done device drivers. Anyway, that is the basic architecture of the internals of the blue pill. And one of the important things to note is that everything inside of here has 3 resources that go to it. There's a clock signal, a reset signal, and a bus interface. Sometimes there's also like a power switch for each peripheral, so you can independently turn them on and off in case you want to have a battery-powered device. You can turn off all the peripherals you're not using, and then it uses less power. But those 3 things, clock, reset, and its bus connection, are what allow these little bits of hardware to do their thing.
How wide are the registers?
They're 32 bits. Yeah, we've got 32-bit buses. There's
Does it have SIMD?
no, not this one. It's got single cycle multiplication and relatively fast division, integer only. There's no floating point unit. Some of the more advanced, the later models of STM32 have some floating point units and some DSP instructions and that kind of stuff. So this is just one of the earliest. The Cortex M3 was like the first of the Cortex M line, and it's sort of a cost-reduced version of it.
So what things did this chip actually power?
This chip has been in everything.
Everything? How long has the chip been out?
So like, I think it's like over like 9 or 10 years now, probably, something like that.
So this has been off the tool.
Yeah, the STM32F1 family chips have been in just any little gadget that needs a microcontroller. Lots of consumer electronics stuff.
Sorry.
One quick interruption. Is there anybody else who would like me to personally solder their STM and deny themselves of the great opportunity? All right, denier of great opportunity, I'm here to help you. Oh, no, you don't know, you're not actually. Okay. Let's just unplug this. Great pain to get that.
Okay, I've got just a couple more things to cover about how microcontrollers work. And this is really important because if you don't understand these things, then it's going to be really confusing when you try and make anything work. So the way that peripherals work and everything works is that they've got these things called control registers, and they are memory mapped into the address space of the processor. So it's a 32-bit address space. That means it's 4 gigabytes large. And we've already said that we've got like 20K of SRAM, and we've got like either 64 or 128K of flash. So what's in the rest of the 4 gigs? Well, mostly nothing. But there are some important regions that have the control registers for these peripherals mapped into them. And you operate on them just like any other memory. You write to an address and it gets stored there, and if there happens to be a peripheral listening on that address, it interprets the 32 bits that got written to it as something that it should store internally and change its state based on. So all of the things that you do to manipulate hardware are by writing values to addresses in memory. And there will be a whole complicated API that we'll introduce later about how to write to those safely and get the correct values written in. Because control registers tend to be broken into fields, and so you've got like a 32-bit value you're going to write, and some bits of it mean one thing and some bits mean another. And in the world of C programming, this meant that you had to, use bit masks and shifting and all sorts of things to build up one of these register values. But we've got handy tools in Rust to make that much easier and less error prone. So another thing that's very important is, I mentioned that everything has clocks that feed it, but the thing about digital logic is that different things built out of logic have different constraints into how fast their clocks can run. So they don't all run at exactly the same clock speed, and it's your job to configure the clocks so that everything has the appropriate clock speed to get the job done that you want to do. It comes up, fortunately, in a usable state. Some microcontrollers don't come up in a very usable state. You have to do a whole bunch of programming whenever you want to do anything. There's a basic setting that will run using an internal, not very good 8 megahertz clock or something like that. But it goes up to like 72, 75 megahertz, something like that. So you can crank the speed way up by messing around with the clock tree. So
by cranking up the clock, you're possibly breaking what you're interacting with?
Not necessarily. The fact that it's a tree means that you've got a bunch of clock sources that you can select from. You saw that on the picture of the board, there's 2 different external crystals. So those can, serve as your main clock source or the real-time clock source. There's lots of things called multiplexers inside, where there's a control register that lets you switch which of the inputs goes to the output of the multiplexer. And there's like several layers of those, and there's dividers and multipliers, and there's a thing called a phase-locked loop, which lets you perform like a pre-division of the clock and then a multiplication so that you can create a wide range of clock rates that the main clock will run at, and then you can divide that down further for the different buses. And sometimes there's like even subsections of a bus that get slower clock speeds because the logic there is deep enough that it can't run that fast. So it's very flexible. There's a lot of flexibility, and it's potentially very confusing. Fortunately, the hardware abstraction layer crate gives you some relatively simple options for configuring it. But you just have to be aware that there's really this complicated structure, and not all values that you can set are actually possible. And so you may not get exactly the clock rate you want if you just put arbitrary numbers in there. And then there's power management, but we don't actually have to worry about that unless you want to do low power mode. And then the final really important thing is pin multiplexing. We saw on the pinout diagram that each pin had like 5 or 6 different options of what it can do. And when you want to run one of those specific peripherals, there's some configuration you have to do to set it to be in that alternate mode that feeds it connects internally the pin to the peripheral instead of the general I/O control. So that's probably a lot, but it will be clearer when we look at the code and get down to actually doing some coding, so now we're at the point where we really need to get everybody to where the debugger is connected. If you already have your debugger connected, then what you'll want to do is get the blue pill base repository checked out.
How late are we going? Are we turning the pumpkins at 9, or can we stay as late as you want?
I'm not sure when they start to kickstart.
Yeah, whatever.
We'll probably
Lights start shutting off at a certain point, but they'll come back on.
we'll probably do like an official close at 9, and then maybe stick around some of us a little bit later. So at the main page here, you'll want to check out Blue Pill Base, and make sure that you've gone through the setup, and you've got the cargo flash, cargo embed, that kind of stuff. Okay, show of hands. Who has their board all soldered and ready? Okay, has anybody got their debugger connected to their board yet? Okay, who hasn't got their debugger connected to their board? Okay, I'll help you. Maybe one of your neighbors can help you get it set up.
So who was this that just gave me this board? You did.
Thank you. Does anybody have an extra Apple?
You do have
dongle?
a debugger.
So actually, I didn't bring mine.
I got one.
Yeah.
Just to connect to the guest.
So you've got the pins.
Thank you.
Yeah.
Enough to where you
go power on. Yeah, it doesn't show up.
Can you see it?
Random people find it anyway. I don't know how, but
Yeah,
I stand that for you. Okay, anybody else who hasn't got their debugger hooked up to their Blue board yet? Okay, is there anybody who hasn't downloaded the Blue Pill base repository yet? Yeah, Blue Pill base.
While y'all are taking a minute to do that, I'm going to pass around a box that has fun things in it. One of the fun things is a tiny little screen. One of the fun things is a buzzer. Another one of the fun things is a gyroscope. I think that's what this one is.
Yeah, it should be a combo gyroscope accelerometer, 6-axis. It's basically the same sort of thing that's inside a cell phone, so you can tell what orientation it's in.
And then a temperature sensor.
So it's a binary temperature switch with a configurable set point.
So I'm just going to pass these around. Just take take one from each bag.
So, speaking of temperature, the analog to digital converter peripheral actually has a built-in temperature sensor connected to one of the channels. So, even though you can't get analog temperatures directly from this external temperature sensor, you can still get temperatures from the blue pill itself. And I actually think the accelerometer thing may have a temperature sensor in it too.
The on-chip one is super accurate.
Oh yeah.
And then we're also going to get you eventually some lights and some LEDs, but those are a little bit more obnoxious to pass around. I need to check to see what else was in the kit that I need to get to you.
Okay, so what are we doing with this space project?
So we're going to do a little walkthrough of it.
Okay.
Is everybody ready for the walkthrough? Okay. So let me talk first about the structure here, because there's a couple of things that are a little bit different that are required. I would recommend starting from one of these points, or there's a number of other places online with templates for different base setups. But I'll talk you through the things that are necessary. First of which is the cargo config. So the .cargo/config. So it doesn't show up in a normal directory listing since it's got a dot in front of it. But this right here, target.thumbv7m-none-eabi, this is what tells it that, or rather the build target down here is what tells it that this is not a native crate. This is a crate that needs to be cross-compiled. One of the software setup steps was to do the rust up target add thumbv7 none-eabi. And this is the line that tells cargo to use that toolchain instead of your native one. Another important thing is we have to give some special Rust flags to tell it how to link these .x files are linker scripts. They allow you to set memory regions. You don't really have to worry about the details of it. The link.x is supplied by some of the like the Cortex-M crate. And then you can set a specific runner here. We're not actually going to use this one, but it doesn't hurt that it's there. When you want to do GDB-based debugging, you can hook it up so cargo run will launch GDB. I haven't spent a lot. I didn't have time to figure out all the different ways and all the different tools that you can use. There's a bunch of extra cool ones that we won't have a chance to cover in here, but I've got some links to them.
So is that like running GDB where it's just a dump of the assembly and the source?
Yeah, you can single step through things. You can hook it up to Visual Studio. There's all sorts of cool things you can do with it. When last time we did this, the tools that we were looking at, like the cargo embed, it had a limited GDB support, but you couldn't use it at the same time as the RTT support that allows you to print things out. So it's easier to get started with printf style debugging. So yeah, we had to use OpenOCD, and that was a whole other setup mess. So anyway, the other new thing here is an embed.toml. This controls the cargo embed program that we're going to use to flash and execute the program and interact with it. It'll pull up a full screen curses-like display where we get prints from the microcontroller. You can set it up so they're interactive, and you can switch, virtual consoles with F keys and have the interaction of different kinds go to different consoles and fun stuff like that. But this configures how to talk to the debugger. We're using the serial wire debug protocol, which is the ARM specified debug protocol. This configures it how to flash. We're telling it what chip we have here, STM32 F103C8. And then RTT here is a protocol extension from a company called Seger that makes the J-Link debug probes. They developed this way to create sort of an in-memory buffer for debug messages in your microcontroller's memory space. And so rather than some of the other ways that you can communicate between a debugger and the CPU, there's like this buffer that requires the debugger to do direct memory reads out of the buffer. You don't really need to worry about how it works, except that it does take a little bit of memory, and it works way better than the ways that they used to provide you to do these things. One of the earlier ways that you may run across in some material online that talks about this is something called semi-hosting that relies on some features in GDB to do printfs and things like that. The problem with semi-hosting is that it only works when you have GDB connected. So if you flash something to it with semi-hosting code and it tries to print to the console and you don't have GDB connected, it'll just halt. Your thing won't work and you won't know why. RTT, because it's just writing into a memory buffer, you don't have to have the debugger connected. It'll just write to it, and if nobody reads it, it's just fine with it. And this will also print out timestamps and all that good stuff. So this is where you can enable Cargo Embed to also start a GDB server, so you can also do GDB debugging. It's a relatively new feature of Cargo Embed that it actually works now, but I haven't had a chance to try it, so I don't know how well it works. So this memory.x here is the final, important thing for what we're doing. This defines the memory layout of the, no, you don't have .x stuff. The memory layout of the microcontroller's memory space. So this is saying that flash memory has an origin at 0x08 and then a bunch of zeros. Its length is 64K. And then the RAM is at 0x2, a bunch of zeros, and the length is 20K. So it's important for every kind of microcontroller that you use that you have these correct, because this is how it decides where in memory it's going to load your program. And if it's not in the right spot, the CPU only looks in one place when it starts up. And if your code isn't there, it's not going to run. And if its idea of where flash or the RAM isn't right, your attempts to modify memory are going to point off into nowhere probably, and you'll get bus errors and it won't work. So not having these set up correctly is a common point of failure. And because these differ amongst all the many varieties of STM32 parts, the underlying crates that supply the other linker thing that's mentioned in cargo config, they'll supply link.x, but link.x depends on memory.x being there in your project. So if you forget to add it, you'll get weird linking errors. And so if you set up your own project and you forget to copy memory.x, you get weird link errors. Just try and remember that that's why. All right, so now onto main, which is where the magic happens. So here we're saying we have a no standard crate, meaning there's no standard library. So you're limited to what's in the core library. Fortunately with Rust, that's actually quite a lot. So you don't get anything that relies on dynamic memory allocation. So you don't have boxes or vecs or stuff like that. But you do have static arrays and slices. Here we are setting up a thing called panic RTT. So RTT is that Seger created debug protocol that allows you to print things to the host console. And panic RTT target means that when your code panics, rather than just silently stopping without telling you why, it prints out a panic message to the debugger console, which is super handy because you will probably panic your code a lot.
So are you saying RTT runs with these generic
Yes.
probes?
Yes.
That's
Their software that speaks the host side of it probably tries to verify that you're using a Seger probe, but this is an independent implementation of it. So it works great. Yeah, so RTT target gives you the rprintline macros and all that good stuff. And
Can we have RTT output the same way you could with Jigger with Setter tools for different color and all that sort of stuff?
I don't know that there's that particular feature supported, but there's a couple of different things that. So Cargo Embed has some formatting. There's a library called dformat, DEFMT, that allows you to shrink the size of your debugging output. So it's not actually sending strings. All your strings are static and shared between the host and target. And it basically gives an index to which string it's going in, and then the things that need to be filled into the format string. And it fills those out on the host instead of on the embedded device, which can speed things up quite a bit, use way less memory too. But I don't know what the full functionality of the Seger's RTT stuff is. It's probably not 100% the same, but I don't know off the top of my head. One of the links that I have in the the resources link on the wiki page will be some probe firmware called Probe DAP or something like that. Anyway, it's a full firmware for a debugger probe written in Rust, and it supports. I don't know if it has to do RTT itself or if the probe RS library just does it, but anyway, it might be interesting to look at. So we're using NB block, and it's a thing that confuses some people, and it will probably go away at some point. But for now, what you have to know about NB block is that the idea was that they were going to enable using async Rust in embedded. There's other projects that have succeeded in doing that, but we're not going to get into that now, unfortunately. But the idea before async Rust existed is that you would write your APIs so that instead of blocking, they would say, oh, I would block. And you have a macro called block that will just loop on the would block result until it gives you a success or failure. So you see that used somewhere in here. Yeah, here. We're setting the timer wait, and then we're blocking on the timer wait, because while it's still waiting, it's going to say, oh, I would block. And yeah, it's just a way of implementing those busy wait loops. And then Cortex M entry gives us this entry macro. So normally in a hosted environment, which is what it's called when you're running under an operating system with the standard library available and everything. There's actually a bunch of code that runs before main, and it's responsible for calling into main. But because we're on an embedded system with no operating system, that code doesn't exist. So we have to use this macro to supply some Cortex-M runtime specific code to call into our main function. And entry tells that code where to jump. And then the most important thing is the STM32F1XX HAL. That's hardware abstraction layer. This provides friendly wrappers around all of the functionality of the microcontroller. We'll, if we get a chance, we'll talk more about that later. But what this code is doing is basically setting up the peripherals to do what we want. Specifically, we are setting up the clocks, and we're getting the clock values out of the clock control registers so that we know how fast it's running. We are grabbing our GPIO peripheral, and we are setting up pin C13 to a push-pull output pin. There's lots of different modes that you can configure pins in, and push-pull output is the normal GPIO output state, where if you tell it to go on, it's going to drive it actively high, and then if you tell it to go off, it'll drive it actively low. We're assigning the push-pull pin to something called LED, and then we're building a timer out of the SysTick timer that comes from the Cortex-M's peripherals. So we showed on that diagram how there was a couple of different buses, and there were things on those buses for controlling external peripherals. But there's some memory mapped peripherals that are part of the Cortex-M CPU itself. And those are what have the SysTick timer. So any ARM Cortex CPU in any microcontroller that uses that CPU will have the same SysTick peripheral. All of the things like how GPIOs work and all that, those vary a lot between different manufacturers and sometimes between different lines of those manufacturers, but the core peripherals like SysTick remain the same. So here we're building a timer that counts in hertz, and we are starting that timer with a timeout of 1 hertz. We're printing to the RTT log hello Rust, and then we're waiting for that timer to expire, setting the LED high, waiting for the timer to expire again, setting it low, and we're incrementing a counter. Every time we increment the counter, we'll print hello again, and how many times it's blinked. And once we get to 10, we're going to panic and say, that's enough. So, just to demonstrate that you get a panic report, because it's unusual for you to get any kind of report like that on an embedded system, unless you're running under a debugger. A debugger like GDB, not like the probe. Yeah?
What is unwrap for? What do you need?
There's unwraps basically assume that the error in a result didn't happen, and if it did happen to happen, then it panics.
Okay.
So I've had it happen a couple of times when I'm messing around with something that's got lots of leads attached to it, and it messes up an I2C transaction or something, and something blows up. I get a nice little panic report if the debugger happens to be connected. So, okay, now for the moment of truth, we're gonna do so I recommend always doing a release build, because that does a lot of optimizations that will cut down the size. If you don't do a release build, often it will be too big to fit in Flash. And even if it's small enough, sometimes it'll be really slow. And then you do cargo embed release. So cargo embed will build it as well if you haven't already built it.
So before it was a cargo build release, right?
Yeah.
Okay.
So you saw there were some, fancy progress bar things. That was the cargo embed flashing your program onto the flash memory inside the microcontroller. And then, well, first it was erasing the flash, then it was loading the new program in, and then we launched it. It set up the RTT connection, and these are the print statements that we had in our code. And so you see here we get a nice report about exactly where in our code our panic occurred, which is a huge help for when your code is being flaky and you don't know why it's panicking. Okay, now that we've got to the point where we can do that, let's have everybody get to that point where you're actually able to flash code. You should be able to see your LED blinking.
So I had a question about the exit. So when this thing panics, the last step is that it sets it to low, and then it crashes. So the release on is low.
Uh-huh. Yes.
Okay.
It's an active low signal.
Okay.
Yeah, in some of I have a bunch of resources in the wiki that talk about different I/O signal stuff and the difference between floating signals and push pulls and active high versus active low. In one of the other crates, I've got something, it's called the switch HAL, and it lets you wrap the pin that you want to control in this wrapper, where you set the mode that the pin is, and you tell it what mode the pin is in, and then you just have to say make it active or make it inactive, and it controls handling the logic of whether that means high or low.
Okay. That's in the wiki, or that's in a crate, but the documentation about
Yep.
active and low is in the wiki.
Yeah, that talks about different I/O stuff that is, there's a whole bunch of stuff about embedded development that is unique to embedded systems development, and dealing with the realities of electrical circuits and the different ways that electrical engineers have figured out how to do things is one of the joys of learning embedded systems programming. There's lots of fascinating rabbit holes that you can go down.
So question about panics. If you experience a hard fault in your Cortex M, does that automatically invoke a panic?
I am not sure what happens with hard faults. So generally you get, so those will trigger an internal, not an interrupt, a condition or whatever they call it. And I think it probably hooks those up to a panic handler.
Because normally in C development, what would happen is you go into an infinite, there would be a generic.
Yeah, your
Number is just an infinite loop. It doesn't do
Yeah.
anything, but in the Rust world, I'm just wondering if somebody's written a hard fault handler that automatically propagates to a panic.
I'm not sure if they've got that hooked up to the infrastructure that attaches the panic handler to the. There's a bunch of stuff behind the scenes that happens when you load in one of those crates, and I'm not sure what all of those things are. I know that you can hook up handlers pretty easy to any interrupt that you want. So if it's not hooked up by default, you can hook it up without too much trouble. All right. Has everybody got to the point where they can successfully flash the program and watch the output? Let's see the blinking. Anybody having trouble and need help?
I might need a little bit.
Okay.
So when I do cargo embeddings, it says access denied.
Aha. So there, you want to go to the wiki,
Okay.
look at software setup,
Yeah.
and there's some UDEV rules.
Oh.
So paste those into the place that says to paste them and then run the command to reload UDEV. And then you'll have to unplug it and replug it, and then you're good.
Yeah, if it's,
Thought I got
if it's
it.
already plugged in, there's an additional reload step I came across.
Ah,
So I guess plug and replug was
That-
a step I
yeah.
didn't do, but I found it was good software.
Will you add that to the wiki?
So I
I,
didn't see how to edit the wiki.
I think you might have to make a member of the.
Oh, okay.
Should I just drop it
This one? Yeah, that'd be great, thank you.
Do you have breadboard wires over there?
Yes, I will distribute those.
Make sure that's typed right.
Yeah, there's breadboard wires and there's resistors. There's actually, there was a box that I left at home that had most of the resistors in it, and I have a few here.
Let's see.
So for those of you who are unfamiliar with hooking up LEDs to power sources, an important thing to know about LEDs is that they will happily consume all of the current that you make available and burn themselves up. So it's important to use a current limiting resistor if you have a current source that provides enough current to burn them up.
How do you know which resistor or which LED?
What is it?
There's some fancy rules that you can follow if you know the forward voltage drop of the LED. And I think the ones that we've got are pretty standard. They're not going to be like the super high brightness ones or anything. So you could look those up and find those rules. But you can also just hook like 100, 200 ohm resistor or something. And it should be fine with a 3.3 volt source. You can go higher in resistance, and that will just make the LED dimmer.
So 100 to 300 ohms.
Yeah, somewhere in that range is probably fine. I mean, I just hook up whatever's handy. Sometimes it's really dim, but it gets the job
Doesn't
done.
burn out, right?
Yeah.
So I'm just gonna throw some of these out here. Basically, just count off 8. The color doesn't matter, the length doesn't matter. And just pull yourself up. Actually, if you get...
Yeah, actually you want 9.
Oh, 9?
Yeah, the rotary encoder has 5.
Okay. Alright, so pull off 9. You don't want to separate them all, just pull them all. This one I think is already got it.
So that's the box that has the resistors and the rotary encoder.
Alright, is this that last one down? Take it around, or,
Yeah. Count off 9 and then.
On the internet anyway.
So, and I got some more too. So.
Pay attention. There's gotta be something in there.
And then we've got some more that are another type, and we'll take 9 as well.
That's how I.
Whatever the yellow dot there.
Oh, did you not get these?
Yeah, it was over there.
Okay, yeah, so
I know,
actually.
So is 9 the whole rainbow, or is 9 one less than?
It's in here.
Well, that's a good question. I think there's 40 on each of these. Sorry.
That's also one of those.
Oh, okay, yeah, so just grab one of each of those things.
How many different things are supposed to be in there?
Here, I'll grab one of each of those things. Put it right in the last time.
So you want to get your, okay, there you go.
I figured quickly.
Yeah, I've got some.
It's on my now, so it's really hard not to short out the headers there.
All right, so you got, here, one for you, one for you. One for you, one for you.
So jumpers on the blue pill, what they do?
Those are for selecting alternative boot modes.
Boot modes.
Yeah, there's like a built-in serial bootloader so that you can load code over a serial port, but it's way less flexible and convenient than the ST-Link debugger. So
So is that meant for like loading code through the USB interface then?
no, it's for doing it over the serial pins somewhere.
So you bumped up 4 things.
I've never tried to do it on one of these because I've always had the ST-Link, but it's possible to use it. One of the projects in the example links, so in the wiki here,
And then, yeah, I'll take these back and then I'll hand out other ones because it gets confusing between the different styles.
yeah, in embedded Rust resources here, there's a bunch of example projects. And I believe it's this tonari.no. I think they use a blue pill or something similar, and they do their flashing over serial. But there's a bunch of interesting projects here. Some of them use a little bit different underlying frameworks. This right here is sort of the Rust working group official list of awesome embedded Rust stuff. It includes links to some books. It includes some matrix chat rooms that the embedded working group and the people who develop the different HAL layer crates, they hang out there and answer questions. They're generally pretty friendly. There's a bunch of crates here that do handy things. Heapless provides a bunch of common data types that don't need a heap. So you statically allocate the size of your thing and you get something that is mostly like the API that it's based on in the Rust standard library. So you can get a VEC API based on a static allocation.
A quick interruption. Can I grab the leftovers of those, real quick, the mail to mail? Just put those on the table. I'm gonna pass these around, which are the other ones. I just didn't want people accidentally grabbing 18 of one and of the other. So these ones are male to female, so they come in handy too. Just grab nine of those.
Are we using these tonight?
If we get lucky.
So Heapless has things like VEX and trees and stuff like that. And another thing it has is implementations of channels. So if you need to communicate between two different parts of your code, channels can be handy for that. Embedded graphics is very handy for drawing on your display. The MPU 6050 driver is, that's the accelerometer that we've got. So the person who developed this driver did it on a Raspberry Pi, and they used the embedded HAL interface, but the Raspberry Pis have floating point hardware, and so they do a bunch of floating point math in it. I'm not sure how the performance is going to be on soft floating point. Might be fine, depending on what you're trying to do. Anyway, those are all worth looking at. For frameworks and tool sets here, this one called Embassy. That is the embedded framework that's based around async Rust. I think it may currently require unstable Rust to build it, but it's pretty nifty. Arctic here is the real-time interrupt-driven concurrency. It's not a full RTOS, but it is a setup using the nested vectored interrupt controller in ARM. It allows you to safely coordinate a set of tasks without a bunch of locks and things like that. It takes care of a whole lot of the overhead of doing things in a way that Rust considers safe, and setting up various tasks that are directly driven by interrupts. And there's a book that is linked here that describes how to set it up and use it, and also a couple of the example crates that I've got in here. Blue Pill Arctic and Blue Pill UI. Those both use the Arctic framework to manage resources. It's pretty nifty, very low overhead, and you can do worst case execution time guarantees and stuff like that. All right, so anyone who has yet to successfully flash on code?
Some trouble with insufficient permissions.
Okay, that's been going around.
Yeah.
Could somebody who's had that problem come around the table and?
Yeah, there's a page on the wiki.
Just drop a message in the Discord with the stuff I did to get it.
Okay, I'll show you where. If you've got the wiki up, you can go to the. Let's see. So click on like the software setup link. And scroll down to the Flash debug tools. Yeah, you passed it. Okay. Oh, wait, okay.
I did this correctly. I
Yeah,
remember,
so you
I
got
remember
this.
it had to go with.
You've got it built, so yeah,
I wanna
it is a
add
little bit further down. So I didn't pass that one, so you're good. What you need to do is a little bit further down. Yeah, that's just other things in the background that have been updated. So yeah, you need to go a little bit further down. And Linux UDEV rules. You must have because. Yeah.
So again, yet another thing I'm gonna pass around here.
Yeah.
There are,
So you need to
I'm gonna pass these around
this file
one set at a
with
time.
These contents, and then run this command.
Either
and
take
unplug it, replug it, and you'll be good.
a 330, so I'll pass these this way, or take both a 150 and a 200. So the box that had the resistors and the rotary encoders is on the shelf next to where these other things were before I took them off the shelf, unfortunately.
So how many of these do we need?
Just one.
Just one, okay.
That's just
Oh,
for
that's
LEDs.
For those ones. Wait, and we're taking one of each of these?
You take one of each and pass it down that way. You just take one. Resistance is more about ratio than it is about exact quantity for most considerations. So you don't need something that's exactly 200 or exactly 400. You can either put things in series with each other to add them together, or you can, basically, if you were told that you needed a 1K resistor and a 2K resistor, a 2K resistor and a 4K resistor would also work depending on what direction things are going in.
No problem.
So what you're saying is that resistance is futile?
Resistance is not futile, but,
Or is it useless?
No, I get it.
but resistance is mostly about ratios. But in the case of the LED, the resistance is about value.
Yeah, the LEDs have a fixed voltage drop.
And then that's the last thing that I'm gonna pass around, and then y'all have everything.
It doesn't really matter what order you do it, as long as you plug it in again after you do that. So you can unplug and replug it. Doesn't matter.
Is there a good local place to get peripherals? Just or vinyl?
So there's a store called Radio Shack. If you pop in your time
This is
machine.
why I'm asking.
There's a Radio Shack in Washington still.
No, the way that you get this stuff is on Alibaba, and you have to wait 3 months to get it. Or you buy it on Amazon and you pay $30 for something that costs $3.
I don't
Or
know,
you buy a lot of them.
I don't know if it's still there, but there was an electronics store on State Street, like between Provo and Springville.
It's dead,
It's dead?
has been for years. Yeah.
Okay. I've driven past before and I've still seen the electronic sign, but I haven't tried going in there for.
Yeah, you just gotta go back to
Yeah.
the directory you were in and try the cargo overhead.
And the place in Salt Lake.
Wait, what?
There was a place in Salt Lake.
DGP then.
Did they use the wrong resistor?
They were all rip offs.
Oh, that's true, yeah, you can use, if you want something relatively quickly, and you don't mind paying a little bit more for shipping, DigiKey is a good place where you can pay 10 cents per resistor and get all the resistors that you want, and then just pay $7 for shipping, so you go there, buy a couple dozen things, and then the shipping is in the noise.
Yeah, DigiKey and Mauser and, there's a few others, yeah. But
If you ever want to do electronics repair, DigiKey and Mauser are your friends, because they have the parts for your Nintendo, even though they're not under the model number that you think they ought to be.
there you go. Success.
I have successfully ripped apart a Nintendo
Yeah.
with the intent to fix it.
But what kind of Nintendo?
For some reason,
With the intent or
which
the actual success of fixing?
Well, I did fix a GameCube. I tried to fix a 3DS and that did not pan out because
they're not,
the part is so small
it's only kind of a vaguely standardized thing.
that it's not, I could not figure out how to heat the board and keep the board heated well enough to get the solder affixed. Because it's so small that just the ambient
Well,
temperature
the Raspberry Pi,
sucks away the heat before you can get the heat to transfer. So you can't get the solder to melt, no matter how hot your iron is,
They just don't sell them, but
without
there's no such
then
thing.
also,
All the blue ones are.
there's a sweet spot. And there's zero tolerance.
The red one originally by some, I think it was originally.
So I successfully melted 5 different connectors
Yeah.
in different ways.
They have much newer,
I don't want to do it, but they're not good for my job though.
So I'll also now pass down
If you use
LEDs,
the black pill, you would,
take an RGB, take an ultraviolet, I think it's ultraviolet, and then grab a couple of the colored ones.
STM32 F411 or something like that. And there's a couple different black pills, but you pick the appropriate model number and then you use the PAL crate that supports that particular model of microcontroller. And most everything else would work the same.
It's actually the three they're using at the same time.
Oh, yeah, that makes sense.
There's 2 different crates in the list of repositories. There's Blue Pill UI and there's Blue Pill More. They both have code for the Oled Display and the Ability Encoder. That is the Oled Display. I'm not sure if you've got rotary encoders.
That's not red green.
Um,
Okay.
Yeah.
The resistors and all that?
Yeah, anti-squirt C.
Yes.
Were there any left over?
You could
Right
look
there.
at how the OLED is hooked up.
We're just loading up all that.
That's cool.
I would put it on a
If anybody
separate.
wants more, I just.
Wait, did I grab one?
Can we try to grab some?
Sure, yeah.
Sorry, thank you.
So where's this stuff?
So if you look at the actual code
Right.
repositories,
I saw you hold on.
yeah, the Rust, Blue Pill More and Blue Pill UI both have some code that talks to the OLED. So the crate that supports the OLED is called SSD something or other. Well, those are RGB LEDs too.
That's cool.
So a fun thing to do with RGB LEDs is to hook them up to PWM
Oh,
timers
I don't.
and
You
use
just want to do either the
slowly
330 or the
fade them on and
200
off
150.
by changing the duty cycle of the.
I had a box that had hundreds of. But it's sooner the rotary crush. So, this is incentive for everyone to keep coming back to the Rust meetup, so if you do your rotary crush next time. When we have it. I'll try to bring the rotary, I'll put the rotary encoders in my bag, so anytime we have a Rust meetup, you can just say, hey, can you have rotary encoder now?
Meanwhile, if you would like to experiment with a UI that uses the rotary encoder and the OLED display, the Blue Pill UI crate that is in the list of Blue Pill Rust repositories, it has things set up so you can use the embedded graphics simulator. Embedded graphics simulator lets you run it on your PC using SDL. So you get exactly what would be on your tiny little screen on a much bigger screen. And you can use your mouse wheel to simulate the rotary encoder. And the rotary encoder has a push button in it. So pushing any of your mouse buttons works like pushing the rotary encoder. And I have everything plumbed up, so if you build, if you do a cargo run at the top level of the checkout, it will build the shared UI model against the embedded graphics simulator.
I'll let you do
And
it.
you build it builds the cross-compatible
Downside of being
version
in
of
the cycle.
Microcontroller. And that one works with the rotary encoder on the device. I've read a little bit about it, but I haven't tried it yet.
So do you do a lot of, like,
Let's take
off
care
the
of
hardware type of programming here? Because I know you
People
did
do.
it. Oh, okay. You do Rust though, don't you?
So any rhyme or
Yeah,
reason
so
to
there's,
take a particular
most of
LED?
the Rust.
Well, there's RGB, there's ultraviolet,
So,
and there's.
we do Rust for camera firmware, so our cameras are
RTOS itself was in Rust.
closer to computers, four core,
They've since made it since
run an operating system, yeah, like they're not like this kind of thing.
because
I can't wait to go past your house.
Yeah, that's why I used to do hardware when I sort of moved on in my career path, but mine was didn't know what levels of building digital logic, programming chips.
Come to the next one.
I saw
don't.
it on his plugging side circuit stuff, but that was not for
it wasn't
mine.
originally.
But
I don't.
there's a parts list,
I know that.
and it has the model numbers of everything. And this is, these are all super common knockoffs. These are basically parts that were developed by one company, and then every other company in the world clone them and sells them under the same part. And Levi will probably know, is like, if you go with 3.3, it's not gonna mess anything up. That's true. No, you pay for them.
Yeah, okay, cool, cool. So how much are these ones?
No, the whole kit is $25.
I think it's a little bit special purpose.
You want me to give you the Spencer discount?
That is a, no, that's, oh, no, I just wanted this part.
Oh. Oh, okay, you just want that. You don't want anything else. Yeah, I'll give you another one.
Okay.
I built in some losses to the price there.
Okay. I was like, dang it, I need to get my own new one.
No, the first time we did this, I did it for $15.
Right.
And then I decided that with actually the different things that they need and whatnot, that's not.
And I switched to
So
some
this
discount.
part is like so much.
No, I mean, it's on the And then are there instructions on the back?
Yes, so there is a repo. I'm wondering if maybe we could get, let me talk to Levi about it.
I've also tried it now, people have written,
Is it possible maybe you could walk us through a quick demo now of actually how the code functions, just to get things like the heat screen?
Even I was like,
Let's do
might be a
that.
better
That's
option.
all.
They had
People are
numbers
getting
like break-ins in their neighborhood and,
So we're gonna go over how to get the display connected.
and so,
And then I think maybe we'll call it a night after that. Does that sound good?
I could do this all day.
All right,
The
so
time has flown while we've been having fun.
there's two different options here for.
Let me get everybody's attention in real quick. Hey, everybody. Again, so he's gonna go over, Levi's gonna go over how we do the LED, and then we'll call it a night. And we may have a follow-up in a few months where we go over some of the other stuff and maybe have a kid's corner for people that didn't attend this one or something. But he'll go over how we hook up the LCD, sorry, I said LED, I meant LCD, the LCD display with one of the other Kickstart repos or Bootstrap repos. And then after that, I think we'll call it a night.
Okay,
That way
so
you get a little bit more value out of this than just the
okay, we've got two options for hooking up the OLED and the rotary encoder. There's this Blue Pill More, which is just the same, write things based on the HAL layer, and then Blue Pill UI, which uses the Arctic framework, and this also integrates the embedded system or the embedded graphics simulator, so you can develop your UI on the host and then have the same UI model and drawing code run on the microcontroller. I haven't updated this one to use the QEI mode of the timer to do the encoder. It uses interrupts instead. They both work, but you have to plug the encoder into different pins. But the OLED stuff is the same. So we'll look at this one real quick. So hello screen here is, wait, why did it pick the wrong folder? Okay. Yeah. So this looks very similar to the previous one. It was actually cloned and then built on top of the Blue Pill base. You see, we import a bunch more peripherals from the HAL layer. If the docs for this are reasonably readable, although would have been nice to be able to go a little bit more into detail on, how to interpret them, but hopefully with this starter code and looking at some of the other examples, so I guess the thing that you should do if there's something in the HAL layer that you want to use is it's got an extensive examples directory. And you look in the examples directory and it'll show you the most basic way of hooking up that peripheral and making it work, as well as sometimes some more advanced things. So that's how I figured out how to do this stuff. So here's that switch HAL thing that I talked about that is just a crate that wraps a pin that's active low or active high, and it abstracts the difference. So you just make it go active or you toggle it, and you don't have to worry about whether it's active high or low. And then this is the rotary module that I wrote here that interprets the two pins. When you hook it up, there's a clock pin and a DT pin, and those allow the microcontroller to tell what direction and how far you've rotated it. Here we've got static definitions for those pins. So in this crate, we were saying clock pin is PA8, and it's going to be a floating input. The DT pin is PA9. And those correspond to the labels on the side of the board.
And could you bring back up the diagram just for a second to show that and their options?
Yeah, so PA8 and 9 right here.
So those can
PB, yeah.
Those can act as pins, physical pins.
Yeah, these are the GPIO.
Timer channel,
Yeah,
I2C, and CAN bus.
So it's the PB ones, not.
Oh wait, no, 8. So
whoops.
I used PB on the other one. Sorry, this one is PA. The PA8 and 9, and then those are right up here. So those are timer 1, channel 1, timer 1, channel 2. You may be able to do the QEI mode on those two, but my other one I hooked up to timer 4, channel 1 and 2.
And just a quick question. Does anybody understand well enough what was covered here earlier? Now that we're actually in this, I think it's kind of important to understand this specifically. Did anybody earlier understand this well enough that they could give a brief explanation, a 30-second, what we're looking at? Or does anybody understand enough to ask a question about what they didn't understand?
Are you talking about the diagram within there?
Yeah.
This diagram and what it's showing here with the colors and the lines? Yeah, I'll give
The legend right here is the key to it. These identify water, power, and ground. So grounds are all black, powers are all red, although they're different voltages. The physical pin number corresponds to these and how they're numbered in the official documents. Pin name is how it's labeled both on the board and in the HAL files. And these names also come from the internals of the chip in the documentation.
Is there a significance in the orders? So like starting at the very top, CK3, T1, BKIN, and like is there a significance in how those are ordered left to right? Because like CK3, and if you drop down to CK1, the blue is before the orange ones. Does that make sense?
Not really. I think that's just a matter of how they.
So this is not like this happens before that. This happens before that. Because I'm saying like those are down here color wise.
No, that's just because it's how the designer of the diagram wanted to keep things grouped together.
Okay.
They wanted to keep these purple SPI ones together because they figured that those will be used more than CTS and RTS on a serial port.
Okay.
So basically what this is saying, it's kind of, if you can imagine like a maze with a lot of doors, and if you open one door, it opens a pathway to a different part of the maze, but it closes a pathway to a part of the maze that was previously open. So if you just kind of have that mental model, it's swinging doors, and if one door is open, that means another door must be closed. What you're looking at here is groups of pins can have a particular function. So there are, I think, more than one group of pins that can operate that display. In order to operate the display, the microcontroller has to be told, select this functionality for this group of pins. And when that door swings and that group of pins is active, they cannot be used for any other function. And in some cases, other pins are also locked into a particular function. So when you choose one set of functionality, at least the pins that you chose that functionality for are locked into a set of functionality. And potentially some other pins that you maybe didn't need for that are also locked into that functionality.
So I think a helpful thing to do is to start from what you want. In this case, you want it, you know you want to talk to the display, and you know the display uses I2C as its communication protocol. So you look at this, or the more complex version that's in the data sheet, and you see, oh, okay, I2C 1 and 2 are on APB2. And then you say, okay, I want to find the pins that are associated with I2C 1 and 2. So you go here and you see, let's see, I2C, that's this color. And so everywhere you see those colors, you see SCL1, SDA1. So you know those are I2C1 peripheral. But if you look, let's see.
But if you use those pins for that, you cannot use them for
right,
like the timer.
You can't use them for the UART, TX and RX1.
Oh, okay.
And you also can't use them for the timer 4 channel 1 and 2.
Yeah.
So you get to pick one purpose that those pins get to serve. They can be just regular GPIO pins, or they can be the I2C1. But you can do I2C1. See, these have exactly the same name. You can route that peripheral to either pair of ports. And then notice that there's also SCL and SDA over here. This is I2C2. So you just got to figure out which peripheral you want to use, or, you know, what kind of peripheral and what pins are free. That may help you pick between one or two. If you have two things that do I2C, you might want to put them on separate I2C buses just to avoid possible address conflicts or performance problems of, you know, trying to run both of them over the same.
And one thing I don't think is laid out here is some nomenclature that's assumed. I'm not seeing it on any of the maps, but D stands for data, C stands for clock, T stands for transmit or put voltage, R stands for receive.
Unless it's timer.
Sync voltage, except for T, that's timer. So there's a couple of things on here that you might need to Google, but they're very, very common in the electronics world. So you'll see this on any electronics kit you pick up, you'll see these standard, well, pseudo-standard abbreviations.
So in, let's see, we've got this I/O page here. This is the page that goes over what you want to know about voltage levels, push and pull versus open collector outputs, current limits and requirements, single-ended versus differential, synchronous versus asynchronous, and then there's peripherals. We talk about GPIOs and timers, and here when we talk about I2C, this talks about the names of the two different pins. There's a link to an overview of how the protocol works, and then some stuff I wrote about how to do it. There's serial peripheral interface, and these are the names of the pins associated with that. DMA, analog to digital converter, yeah, all that good stuff. So this right here, the peripheral access crate guide, this will be helpful, I think. Yeah, this diagram is new since last time. This shows the internal structure of how it's an auto-generated crate, so you don't, it's hard to find the source code, but it turns out the STM32 F1 project actually checks in for every build the auto-generated code, so you can reference it. So that's pretty handy if you are confused about it and you want to see how it works.
And that's generated from the hardware language, right?
Yeah, there's
HTML?
it's called VSD, I think.
VSD.
It's part of the CMSIS thing that ARM and their captive tools company developed. So yeah, SVD. This defines a way of describing all of the the memory mapped control registers for the peripherals. And you can see here all of the peripherals that are in here. So this includes the whole family, so some things are going to be listed here that aren't actually in the blue pill. But if we want to do like I2C1, you can see what all the registers are. And this shows there's a register called CR1. This is the offset from the base of the register block. These are what all the different bits, you'll see that there's 32, and we're only looking at the lower 16, and these are the names of the individual bits.
So in order to connect the screen to the IC2 bus, we need to have, there was PA8 and PA9, or no, that was
for this crate, we were using PA8 and PA9.
Okay.
So I think
No, that's the encoder. The screen goes to, where did I put this? It's probably, no, it's in here somewhere.
And if you actually
Yeah, here's SCL and SDA. So it's pins 10 and 11. So it's B10 and B11.
Okay. And we have the option of choosing B12 and B13 as well if we were using a different configuration. But for this code, that's what it needs to be set to.
Yep. So
which one was the clock again?
you can tell from right here, SCL1. Or no, we said 10 and 11, right?
So I think we're over here. Yeah.
Yeah. So yeah.
So those are the two
PB10,
pins
PB11.
that need to be connected to the display. And then the display, what was the voltage on this?
It's 3.3 volts.
3.3
so you've got
volts.
3.3 in ground. Just next to the data, there's the reset line, and then there's 3.3 volts, and then there's ground. So clock data, skip a pin, 3.3, and ground.
So does the display already have hardware pull-ups on it?
I believe it does.
GPIOs so that they have pull-ups?
I think the hardware has pull-ups. It works without configuring them anyway. I'm pretty sure I checked that at some point, but it's been a while. Okay, so once you've got it connected to the physical pins, these two lines configure it into one of the things that's noted about I2C is that it's a bus protocol, so you can have multiple devices on the same bus, which means that you have to run them in open drain mode. That's what these lines do. And then this chunk of code right here wraps those pins in the blocking I2C interface. And this is the object that gets passed to the display controller, which is the SSD1306 here. So we've made the I2C display interface that comes from, is this from the, yeah, that's also from the SSD1306 crate. So you got to wrap the bare hardware abstraction layer interface with this struct, which interfaces it to the SSD1306 library. So this, you got to pass it the interface, and then you've got to pass a display size, and these are 128 by 64. And then you can tell it whether you want it to be rotated or not, and we're saying no. Rotate 0. We put it into buffered graphics mode. And then we call init. And then after every set of commands, you've got to call flush. So this hello display thing is the code that is not dependent on any of the hardware, and it's also not dependent on whether you do it in. It'll build on both for both the microcontroller and the host environment, and this is what actually does the drawing and modeling of the display. And right now it's kind of a dumb thing that just says hello Rust, and it prints out a counter that corresponds to how you've rotated it. And it makes a ball that falls from the top to the bottom and wraps around, and it moves from left to right as you rotate the knob. And I can actually show you what that looks like through the magic of the So this is what it will look like. As you rotate the knob, it'll count up, and it'll wrap from top to bottom. Change the counter. And then when you click, it'll print. So if you want to be able to do the development and of the UI on your host with the embedded graphics simulator thing like this, use the Blue Pill UI crate. There's a lot more involved stuff going on in this crate to try and keep the hardware setup separated from the graphics stuff and the controller.
I was trying to get the virtual display to work, and it seems like there's
some more dependencies that you need for that. It's mostly libSDL. Just app search SDL2, I think, will get you. So if you're using the Blue Pill UI crate, you can go into the cross directory and you do cargo embed release in there, and that will run the same UI code on the Blue Pill. So you probably can't see it, but yeah, you can come by and check it out.
So are you saying you got that thing connected to your mouse somehow? Is that what you were saying earlier?
Yeah. If you do, so that's in the Blue Pill UI crate rather than the Blue Pill More. There's way more stuff involved in it, so I figured we wouldn't get to it, but it's a handy way to show what it'll look like. They use the same UI drawing code. There's just more fancy stuff in the Blue Pill UI crate. So yeah, if you want to see how it works, you can come by and see it. Through tiny screen, so yeah, I've got this one set up to where if you push the button, it prints out to the console what number it is.
So if there's anybody else that would like your stuff soldered, speak now or forever hold your cheese.
Yeah. So yeah, you could set up like a. So these ones have like some yellow lines at the top, and then the rest of
Where
it's
they're always yellow, they're
Yeah.
uncontrollable.
Yeah. So I have these old Sansa MP3 players that have a screen a lot like this, and they use yellow bars on the top for the like the battery indicator. It's like a menu bar on top, and then they have like the printout of what's playing and stuff like that beneath. But yeah, you can print out, current temperature. There you can plot lines, so you can draw, the history of some value over time. There's all kinds of interesting things you could do with this basic setup. And I look forward to hearing from everybody about the cool stuff that they have done with their Blue Pill. So if you do mess around with it, let us know on the Discord what you do with. And if you have any questions, I'm happy to answer those there.
I'm gonna make something that senses human emotion.
There was like some Google AI kit that they sold at Target that it had a Raspberry Pi and a camera module, and it was supposed to detect your emotions. It kind of worked. It could tell if you were smiling. Crazy stuff.
Amazon packages to your house based on your mood.
Yeah. But there are some, in those resources links, there's some interesting projects that people have done that you can look at for inspiration. The Tonari one is pretty cool. They they basically use very similar hardware where they've got a rotary encoder, and they use it to control some multicolor LED lighting, and I don't remember the other stuff it does, but
One good project is an RC car. They all use basically the same chips. You just look at the data sheet, the chip, and you can either connect it straight to the car, so you have it on the car, or the chips are basically the same.
so what I like about this write-up is that they show the whole progress of how they started out with a Blue Pill board or something like that. And they take it all the way from just flying leads on a Blue Pill to solderless breadboards, to soldered breadboards, to custom PCBs. Yeah, it's all based on a Blue Pill. Yeah, this is their first. This is actually a black pill, I think, but they switched to a Blue Pill at some point. Anyway, yeah, they're controlling these. They've got a fancy rotary encoder with an LED that they can change the color on. Anyway, that's, I think, all we've got for now. Ah, well, that was a little bit more successful than the last time I did it.
I would say so. We got further, more people were prepared. Only that I left the rotary encoders on the shelf. That's the one thing that would have been, because I think we would have been able to use the rotary encoders tonight.
Once again, let down my leadership.
Yep.
And I got the screen working.
Yeah, I think that's
Oh,
great.
sweet.
You got the screen working. By the way, if you want some extra stuff,
Nice.
some extra wires, some extra resistors, some extra LEDs, feel free. I just wanted to give a number so that you could make it around the table and everybody could get something, and rather than just say, here, take some. But if you feel like you want more or you need more, then please do grab on your way out.
So if you want to play around with the screen, I recommend looking at the docs for the embedded graphics crate. They really good documentation, and there's links there to other projects that are built on top of embedded graphics that you can experiment with. They've got there's some simple layout libraries that help you position your shapes. You can draw, circles and squares and rounded rectangles, and you can do filled lines and your basic vector graphics primitives.
Good. Hopefully you still want to.
Of course, there's a number of different fonts you can use for text.
Okay, so I'm going to wrap this up. Thank you again, Levi, for putting this together for us, for doing all that research. And I don't know if y'all can grasp the gravity of. I know this is a lot of information. I know that it felt probably pretty daunting, and a lot of it went 747 on you. But that wiki that he has put together is of phenomenal value. So if you, it's fine if you felt like, oh my gosh, I learned almost nothing, there's just too much. As you get exposure to the vocabulary and how to do basic things, just kind of look through the code, try to figure out if you can get an LED working on one pen, if you can change that pen to do a different pen. But the documents that he's put together, going through all those different sources and getting that stuff in one place, is pretty much a miracle. So if you do continue down this road, you will reference that again and again and again. And like I said, hopefully we can have a part 2 in a few months, and then do maybe go a little bit more into the really, really, really important piece once you get past these demos of how do you actually change a pen to do something that it didn't do before. With all that said, I want to also thank Vivint for hosting us here. I'm going to come around here maybe so I can be in front of the camera and say that. So we're really grateful to Vivint for hosting us all here. And like I said, Levi, and for those of you that are joining in online, if this was useful at all, if it was, if you got something out of it, consider a like and a sub to the Utah Rust channel on YouTube. And the pizza was courtesy of Vivint. The hosting was courtesy of Vivint. I just make sure I plug Vivint. And are you hiring?
Of course, always.
What are predominantly the languages and positions you're hiring for right now?
I think we do have some Rust right now, but primarily a lot of Go, Python, depending on the team. I'm sure there's stuff on the IT side that's .NET, but
so if you're proficient in Go and or Python and like dabbling in Rust,
yeah,
Jeff.
Come say hi.
And again, if you want to grab any more wires or LEDs or resistors on your way out, I'd be happy to give you some. And hit me up at one of the Rust meetups, and I'll carry the rotary encoders in this bag. When I get home tonight, I'm going to put them in this bag, and they'll stay here for a few months. So,
if there's anything that you want to see next in the materials in the wiki or examples, let me know.
Who are you on Discord?
I think you're just under Levi on Discord.
Yeah, I think I'm always either Levi or Peniel Servo.
Oh, you have the servo.
Yep.
Okay.
And a special shout out to Spencer, because he's a good friend of mine.
Oh, okay.
We hang out all the time,
Sometimes on YouTube.
at least once a month, at these meetups.
Exactly.
All right, I'm gonna end the stream. End stream.